Okay, so blah, 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 blah. So the functions that we're studying in this chapter are inverse functions. Those are the ones that we skipped. And so they want to just make sure that we understand a little bit what an inverse function is to start with. So super, super simple. Let's say that you were measuring the bacteria in a petri dish or whatever as a function of time. So you, every hour, looked at the stuff in the petri dish and counted how many bacteria there were, right? So then this would be the number of bacteria as a function of time t. Well, then you could also flip this around, because if you found a relationship between the time and the number of bacteria, you could say, oh, I could do that backwards. I could also just go now and redo the experiment and count the number of bacteria that are in a petri dish, and based on that I could figure out how long the bacteria have been in the dish, right? So you just take the thing and you flip it around. And so the notation, this is n equals f of t, and then if we do the inverse, that is this little -1 thing. And so you guys recall that that -1 does not mean the function to the -1 power. It's not 1 over that function. That means the inverse. You go the opposite. Okay, you switch the x and the y. So here's some other more fun visual ways to look at that. Also remember that not all functions have inverses. So this one, for example, since if you plug in 3 to this equation, you get 4 as an answer apparently. And if you plug in 2, then you also get 4. That's fine. You can get the different answer. But if you go backwards, then that would mean that when you plugged in 4, you weren't sure, you wouldn't be sure if you would get 3 as an answer or 2 as an answer. So this one has an inverse because everything gets mapped to a unique value, but this one does not. Okay? Functions that have inverses are called one-to-one because every one of these arrows goes to one individual point. Functions that don't have inverses are called not one-to-one. Yeah. Okay, it's not like 2-to-2 or 1-to-2. Or, yeah. So here's our little definition. You probably don't have to write this down. A function f is called a one-to-one function if it never takes on the same value twice. Okay? So this function, for example, is not one-to-one because if you plug in this, you get that answer, and if you plug in this, you get the same answer. What's that? Right, so you can't do the inverse of it. So another way to think about this is you know that this is a function because it passes the vertical line test, right? To tell whether it's one-to-one or not, you would look at it and decide whether it passes the horizontal line test. So if it passes the horizontal line test, then it is one-to-one and its inverse will be a function. If it fails the horizontal line test, oh, there it is, then it's not. Okay? Yeah, fun stuff, cruising through this. Okay, so for example, is the function f of x equals x cubed one-to-one? So we're going to look at the graph. And you guys all know what the graph looks like. Do it. Okay, so does this pass the horizontal line test? Yes, the horizontal line will never cross this graph more than once, right? So that means it's one-to-one, and so that means that its inverse would also be a function. How about our old friend g of x equals x squared? Is this function one-to-one? No, because the horizontal line passes more than one point lots and lots of times there. And if you did the inverse, if you solved it, it would be plus or minus the square root of x. And so then it would look like this, and then that would not be a function. Yeah. Okay? Because of the whole plus or minus thing when you take the square root. Okay, one-to-one functions are important because they are precisely the functions that possess inverse functions according to the following definition. Yeah. Who cares? And then when you do the inverse, you switch the domain and the range of the two things. Remember that? Because you're switching the x's and the y's. So the domain of the original becomes the range of the other one. Okay, we talked about that already. If you see this to the -1, that does not mean raise it to the -1 power. It's not 1 over the function. If you wanted to do that, you would write it in this super complicated, funny way, which we probably won't ever do. Okay? All right, not calculus today. Okay, so here's a fun one. If you can get these correct, then you're in really good shape. So if we know that f of 1 equals 5, f of 3 equals 7, and f of 8 equals negative 10, what is f inverse of 7, f inverse of 5, and f inverse of negative 10? Right. You just switch them around, right? So f inverse of negative 7 is really saying go backwards, start here and go there. So f inverse of 7 is equal to 3. And f inverse of 5 is equal to 1. And f inverse of negative 10 is equal to 8. Okay? So you're just going backwards there. Just a little notation. Wow, lots of fun things. Yeah, so this should be sort of self-explanatory. If you take the inverse and you plug it into the original function, since they're inverses of each other, everything will just cancel out, and you'll just be left with x, right? Or if you take the original function and plug it into the inverse, same thing happens. Everything cancels out, and you're just left with what you started with. Yeah. Okay, how to find the inverse of a one-to-one function. Do you remember this? You remember doing this? So give me a super basic function. Okay, y equals x cubed. So the way that you do that is you switch the x and the y. Remember? So you rewrite this as x equals y cubed, and then you solve for y if you can. How would you solve that for y? Cube root both sides. So for this one, the inverse would be y equals x to the 1/3, or y sub 3, depending on how you read my fraction. Okay? All right. Okay, so do this one on your own. Find the inverse of that. Borsky, do this on your own. Don't just sit there and look at the screen. Do it. Jake, you're not even watching this video, so why am I talking to you? Do you? Yeah? Yeah? Yes? Okay, then if you think of these graphically, again, I don't know if you remember this, but when you switch the x and the y on the coordinate plane, if I start with the point maybe A, B, I guess, and then switch that around to go B, A, then what you're doing essentially is you're reflecting that point over the line y equals x. So a function and its inverse, another way that you can find it graphically is if you just take these and reflect it over the line y equals x. That's that. There's a line of symmetry there between those things. So that is fun. Yeah. All right. Okay, so next one, sketch the graphs of f of x equals the square root of negative 1 minus x and its inverse function using the same coordinate axes. So how do you want to look at the graph of the square root of negative 1 minus x, do you think? It's the root x is the parent function. Yeah. Is it though?
But it's flipped though. Negative and negative.
Yeah, I think we're going to go with what Cameron said. We're going to start plugging in some numbers, but I think really what's happening here is if I factor out a negative 1, then I have the x plus 1 like that. So really what I'm doing is, I think, taking the regular old square root function, the plus 1 moves it to the left 1, and then this negative 1 inside here flips it. Does it flip it upside down, or does it flip it side to side? Inside the parentheses is always a left to right thing, yeah, so it's going to flip it side to side. So it's, Logan, you have the graph. Does it look like that-ish? No. Oh, it goes from, oh, right. No, it does go from negative 1. So we flip it first and then move it. Okay, so if we... Right, got it. So if we just wanted to check that just to make sure, like Cameron said, you can always just plug in numbers if you wanted to. So what's the easiest number to plug in there? Can't plug in 0 because then I'd be trying to take the square root of negative 1. Can't plug in 1. Can't plug in 5. Can't plug in 6 because I'm getting negative numbers. There we go. How about negative 1? Because if I plug in negative 1, then negative 1 plus 1 is 0, right? And the square root of that is 0. So we're going to start at negative 1, 0. What's another number that you know the square root of?
2.
You know the square root of 2, really? Huh. Plug in negative 5 because then if I plug in negative 5, then negative 5 is plus 5, and then the minus 4 makes that be, minus 1 makes that be 4, and the square root of that is 2. So 2, 3, 4, 5, yep. Where's the one that we're missing, just for funnies? So you're going ahead now. There's a point in between here that we don't have. Right, the square root of 1 is 1, so how do I get this to equal 1? Yeah, negative 2, so if I also plug in negative 2, then I get 1, and that's right here, and that matches what Logan has on his calculator. All right, so now if we want to sketch the inverse, maybe you're really good at this, maybe you can like visualize what that's going to look like. Can you sort of tell me like when I flip that over the thing where it's going to go? 0, negative 1. And then where's it going to go? Like this? Ish? Yeah, okay. So that's what this looks like if you reflect it over there. Or Mackenzie's like, duh, we have the x's and the y's right here. Yeah. So why don't we just flip those around and then I don't have to worry about it being too skinny. Negative 1, 0 becomes 0, negative 1. Negative 2, 1 becomes 1, negative 2. And negative 5, 2 becomes 2, negative 5. Yeah, kind of trying to get the concept thing first, and then we can get the actual real what the thing looks like. Okay. 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 So let's talk briefly about the calculus of inverse functions. It says, now let's look at inverse functions from the point of view of calculus. Suppose that f is both one-to-one and continuous. We think of a continuous function as one whose graph has no break in it. Since the graph of f inverse is obtained by the graph from the graph of f by reflecting it over the line y equals x, if the original function has no breaks in its graph, what's going to be true about the inverse function? It's also going to have no breaks, okay? This geometrical argument does not prove the following theorem, but at least makes it plausible. If you would like, you could find a proof in Appendix F in your book, okay? But this theorem says that if f is one-to-one and continuous, then the inverse is also going to be continuous. No big deal. Okay, now suppose that f is also differentiable. What's going to be true about the inverse? Let's just cut to the chase and save all that crazy reading. It's going to be differentiable as well. Yeah, so they have a little graphical example here. If you can find the tangent line at a particular point, then when you flip that around, the tangent line is going to exist also there. But there's also a relationship between the slope of this tangent line and the slope of this tangent line. They're what? I don't believe that they're opposite because they're both positive, right? So they're not opposite, so it's not that simple. It's actually sort of a complex little formula. They would meet, yeah, somewhere down here. Here is the first thing from this section that you should write down. If you have a one-to-one differentiable function and you know that it's inverse, then the way that you can find the value of the derivative of the inverse is you go 1 over the derivative of the inverse at that particular point. And we'll do, of course, an example here in a minute. And then here's a little proof if you want to brush up on your limits, kind of think your way through that a little bit. Then there's Logan, who's still writing f prime. And this is the derivative of the inverse at a particular point. Ready? Ready now? Ready now? Now? Yes. Feel sorry for my wife. You saw what? Did you?
I saw a video of a little piggy bank that was a cat in a cardboard box, and they put the coin in there, and it would drag the coin in like.
Oh yeah, I've seen
and
them
the
before.
other cat in the background's like, what is going on?
Okay, I thought we were going to do. Okay, so here we go. So if f of x equals 2x plus cosine of x, find the value of the derivative of the inverse at x equals 1.
I thought you were reading off the button, but it was not.
Right, so here's what we know. Sort of relate it to the definition that we just had up there. A is equal to 1. Okay, what else do we need? We need the derivative of the original function. So f prime of x is, and so this is what I was talking about at the beginning of class. You get to sort of use the things that you've learned before. It's going to be a little bit confusing because we're going to have derivatives and integrals like together in the same section. So it's hard to remember when you're doing what. But the derivative of 2x plus cosine of x is 2 minus sine of x. Okay, good. And then what else do we need for that formula? The inverse, okay? Now, if I tried to find the inverse of f of x equals 2x plus cosine of x, the way that I would have to do that is I would switch the x's and the y's. Don't write this down. X equals 2y plus cosine of y. And then I would solve that for y, right? That's impossible because of the trig function and the algebra function, the linear function together. You can't solve that for y. So we can't actually find the inverse, okay? But what we can do is we can find the value of the inverse at 1, okay? So what you have to ask yourself is, you don't set it equal to 1. You have to ask, well, yeah, I guess you do set it equals to 1. What do you plug in here to get 1 as an answer? Wrong. Back of the class. We want it to be 1, not negative 1. 0, good. F of 0 equals 1. Okay, because if I plug 0 in there for x, 2 times 0 is 0, and the cosine of 0 is 1. So they're always going to sort of give you these that you can figure that out sort of with a guess and check relatively easily. So that means that f inverse of 1 is 0, and that's what we need to know mostly for our formula, right? Okay, so what was the formula for finding the derivative? That's the inverse, yeah. F of 0 equals 1, so nope, that's a negative 1 right there. 1 over f prime of the inverse at that point, right? Okay, so we got to start in the middle and work our way out. So what is f inverse of a in this case? 0, because that's what we just figured out right here. Does that make sense? Yeah. Okay, so I want 1 over f prime of 0. So here's what the derivative is equal to. So if you plug in 0 there, what do you get? 2, because the sine of 0 is 0 and 2 minus 0 is 2. So it turns out that our answer is 1/2. Okay, that's a little wacky. It's more complicated than it should be. That's the answer, yeah. So what we did is we found the value of the derivative, found the value of the derivative of the inverse function at 1. And the reason why it was so complicated is because we couldn't just find the inverse function, take the derivative, and plug in 1 because we can't find the derivative, I mean the inverse of this function. You know what I'm saying? So you had to use that formula instead. Okay. Huh? Nope, isn't 1. So we figured out a is 1 because that's the point they asked us about, right? We figured out what the derivative of the original function was because we needed that for this step here. And then we did this little game here where we figured out what value could we plug in to get 1 as an answer. Okay? So I took this and plugged it into here. That's the answer to the insidemost part. And then I plugged that into the derivative, and then 1 over that is my answer. Okay? Okay. Whoa! What? Really? Yeah, why not? It's not really that bad. Cameron's giving me that. Really? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Some people said, hey, I want to be prepared for college. So, you didn't say that? It's not that bad.
I just don't want to be in like math 90.
No, you will not be in math 90. You won't be in math 90.
Do they kick you out if you don't get high enough physics scores?
Kick you out of the school? No.